This video is on periodic trends of atomic size and ionization energy. So we're going to start with Coulombs law because really that is going to govern our trends and how atoms behave. It's all about how a positive nucleus is attracted to our valence electrons, or really vice versa. So Coulomb's law says that attractive and repulsive forces depend on two things. They're going to depend on the charge. So if they have the same charges, they're going to repel. Opposite charges, we're going to attract. Since we're talking about valence electrons and a nucleus, we're going to talk more about forces of attraction, but it also works for repulsive forces as well. The greater the charge, the greater the attraction. So if you have one positive attracted to one negative, you've got a certain level of attraction. If you have a lot of positives attracted to a lot of negatives, you have a greater attraction according to Coulomb's law. The second thing that attractive and repulsive forces depend on is the distance between the charges. The greater the distance between two charges, the lower the attraction. So those two pieces really can explain all of our periodic trends. And first, we're going to apply that to our atomic size of atoms. So here I have a hydrogen atom, and I have my one positive proton attracted to my one negative electron. We only have one energy level on this atom. If I look at helium, helium still only has one energy level, but it has two protons in the nucleus, and we have two electrons there on that first energy level. Because our charge, the magnitude of our charge has increased, we now have two positives attracted to two negatives. The attraction is greater. And I tried to reflect that here in my drawings. It consequently makes helium a little bit smaller because the attraction is greater. It kind of pulls in those electrons, those valence electrons, a little bit more. All right, so now let's look at something with three protons. So lithium is here. It has three protons, but you'll notice now we're on the second row of the periodic table. We've got two energy levels. And so what happens here is the distance between that positive nucleus and that negative valence electron has increased. And so there is less attraction here than there would be for hydrogen. And so the atoms get larger the more energy levels you have. Well, now let's talk about things with two energy levels. Something with four protons would be beryllium. And now we're going to start to see the same thing that we saw when we compared hydrogen to helium. We get a more positive nucleus. Electrons are, again, still on the second energy level, or valence electrons are still on that second energy level. And they are going to be more attracted to each other than lithium because there is a greater magnitude of that charge. We get a more positive nucleus, we have more attraction, and beryllium ends up a little bit smaller than lithium. We can see that pattern continue with boron. We have 5 protons in the nucleus. We still have 2 energy levels, but the electrons, those valence electrons in that second energy level, are more attracted because we have a more positive nucleus. So the magnitude of that charge is going to play a role here. Then we've got carbon, which is even smaller because we have an even more positive nucleus. And nitrogen would be even smaller than carbon. Again, still 2 energy levels, but we're going to have 7 protons in the nucleus. And so that we have a more positive nucleus. Those electrons are just pulled a little tighter in towards the nucleus, making nitrogen even smaller than carbon. And it goes on like that as we look across the periodic table. All right, so the way we measure atomic size is we're going to measure the atomic radius because As we know from math class, from the radius, we're also going to be able to get the diameter, and then we would know the size. Well, measuring the size of an atom actually ends up, or even the radius of an atom, ends up being kind of difficult because it's hard to tell where an atom actually ends. It kind of just fades off into oblivion. Remember the electron cloud model. It's hard to tell where a cloud ends. So what we end up doing to find the size of an atom is we take two identical atoms that are bonded together, and we're going to take half the distance from between the two nuclei, and that gives us the atomic radius of a particular atom. Here's a nice visual, so we can look at the atoms and a little, instead of my drawings, we can actually see some representations. So we have hydrogen, still kind of a tiny atom, but helium's a whole lot smaller. And then we can see as we get another energy level, because again, we've gone to row 2 of the periodic table, the atoms get larger. And then as we go across, because we get a more positive nucleus, those atoms get smaller and smaller, and that trend repeats. So as we go down a group, they get larger, and as we because we add energy levels, and as we go across, the atoms do get smaller because we get a more positive nucleus. So I would recommend that you write on your periodic table or on a sticky note that you can apply to your periodic table these trends. And we're going to add several to them, so don't write them as big as they are here, but an arrow showing what happens to the size of the atoms as you go across. You would want to make sure that you included the reason why in your notes. So don't put that on your periodic table, but you can see as we go across, the atoms get smaller because we get a more positive nucleus. And as we go down any group, the atoms get larger. And that's because each time we go down a period, we end up with more energy levels. So the atoms are further apart from the nucleus. Okay, so I'd like for you to try and put these elements in order from largest to smallest. This is a period trend. It looks like we're going across a row 3. So we're going to start with the largest and go in order to the smallest using our trend. The correct answer is this. So we have sodium as our larger atom, and as we go across, we get a more positive nucleus. So then aluminum would be the next largest, then sulfur, and then chlorine would be the smallest of those listed. Then I have a this is a group trend, and this group is group 15. So put these in order from largest to smallest. All right, in a group trend, atomic radius increases as you go down. So the largest atoms are located here at the bottom. So it's going to be bismuth, arsenic, phosphorus, and nitrogen would be the smallest there with only 2 energy levels. All right. Now, again, Coulombs law. Remember the 2 things that attractive and repulsive forces depend on. They depend on the charge, both what the sign is or the type of charge and its magnitude, and then the distance between those charges. It can be used to explain all of our trends. So our next trend is ionization energy, and the word you should recognize from ionization energy is the word ion. An ion is a charged atom. So ionization energy is the energy it takes to make an ion. It is the energy required to remove 1 electron from a neutral atom of that element. The trend we're going to be dealing with is the first ionization energy, represented by I sub 1. And I1 is the energy required to remove just the first electron from a neutral atom. We'll talk about other trends of the periodic table. So we'll talk about removing more than 1 electron here in just a little bit. So if I wanted to talk about removing the second electron, it would be I2. If I wanted to talk about the energy it takes to remove a third electron, that would be I3. So the trend we're going to learn, though, our basic trend is just the first ionization energy, the energy required to remove just the first electron from a neutral atom. All right, so with first ionization energy, there is a greater attraction between the nucleus and the valence electrons in small atoms. Because those electrons are more attracted, they are going to be more difficult to remove, so your ionization energy would increase. The reason the attraction is greater is because there's less distance between those charges in small atoms. There's going to be lower attraction between the nucleus and the valence electrons in big atoms because there's more distance between the charges. If there's lower attraction, there's lower ionization energy. It takes less energy to remove it because it's not as attracted. Now, if we look at the periodic table, we try and see which group of this, and we try and look at it logically, which group does not want to lose any electrons. Well, that would be our noble gases. Our noble gases have that magic number of 8 and are happy and stable. They don't want to lose any electrons. So these guys are going to have really, really high ionization energies. The halogens have 7 valence electrons. They don't want to lose an electron. They want to gain one so they can have that magic number of 8. So halogens are still going to have really high ionization energies. Over here in group 1, though, they're going to have pretty low ionization energies. As far as groups go, they're going to have the largest atoms for each row. So there's already less or more distance between the nucleus and the valence electrons. So there is less attraction, making it easier to remove. So again, we've got hydrogen attracted to, or we've got a positive nucleus, proton attracted to 1 electron for hydrogen. So there's a certain ionization energy associated with this on how difficult it is to remove that electron. When I have helium, helium has a greater charge magnitude. The distance is the same, but the electrons are more attracted to this more positive nucleus. So the ionization energy is going to be greater. It's going to be more difficult to remove an electron from helium than it would be for hydrogen. If we look at lithium, lithium has 2 energy levels. This electron is further away from the nucleus than it was for hydrogen, and so there's less attraction. So this, the energy it takes to remove 1 electron, and it would be the valence electron here, is going to be lower than that of hydrogen because the electron's further away. Then as we go across and have a more positive nucleus, our electrons become more attracted, and so our ionization energy increases as we go across. And nitrogen would have an even greater ionization energy than carbon because it has a more positive nucleus. There's more attraction. So as we go across, ionization energy increases because I get a more positive nucleus and there's more attraction. Then ionization energy decreases as we go down because as we go down, we add energy levels and the electrons are further away from the nucleus, so less attracted in these giant atoms down here. And so that makes it easier to remove. So I have some practice here. Putting elements in order from smallest to largest. Ionization energy. A is a period trend. And I think we're dealing with period 2. So we're going from smallest to largest. So these would have atoms over here would have the smallest ionization energy because they're the larger atoms. And then as we go this way, our ionization energy is going to increase. So the correct order is this. The next one is a group trend, and it has to deal with the halogens over here. As we go down a group, ionization energy decreases. So the smallest ionization energy is going to be the one closest to the bottom. And then as we go up, our ionization energy is going to increase. Fluorine is going to have a really high ionization energy. It's a really small atom with only 2 energy levels, so those electrons are really close. And it has a very positive nucleus for the number of energy levels it has. So it would look like this. Okay. So make sure you do write that trend on your periodic table along with your atomic size. So atomic size decreases as you go across, your ionization energy increases. And then as you go down the group, ionization energy decreases, your atomic size increases. All right. Now, dealing with ionization energy, if we try to remove more than one electron, for each additional electron that is going to be removed from an atom, the ionization energy increases. Always increases. The number of protons isn't going to change. And as we remove electrons, the remaining electrons will be more attracted to that nucleus because I still have the same number of protons. And so now I have less electrons, that's going to make them more attracted. So if you, I2, removing the second electron, is always larger than I1. I3 is always greater than I2, always. Core electrons are more difficult to remove than valence electrons. That is because they are closer to the nucleus by a whole energy level. And so they're going to be more attracted since they're closer, according to Coulombs' law, and so they're going to be more difficult to remove. If we have a list of ionization energies for an atom, you're going to see a large jump in the ionization energy when core electrons begin to be removed. I'm going to go to a different slide here. This one. Okay, so here I have these elements of row 3 of the periodic table, and their first ionization energy. So just removing that first electron, so you can see as you go across the periodic table, in general, because these are general trends, our ionization energy does increase as we go to those smaller atoms there with more positive nucleus. Now let's look at aluminum here. Aluminum has a certain ionization energy for removing that first electron. When I go to remove the second electron, it requires more energy. The third electron is going to require even more energy. And then you have this huge number. So we went from 500 to like 1,800 to 2,800 to 11,000. That is a huge jump between the third and the fourth ionization energies. Remember, aluminum is in group 13, so it has 3 valence electrons. And so these first, second, and third are all removing valence electrons. This energy right here is when we're trying to remove the fourth electron, which is a core electron. And so if I just saw these numbers and I didn't know what the element was, I could say just by looking at them, ooh, there's a big jump in ionization energy. So that fourth electron must be a core electron, and these guys must be valence electrons. This is an element from group 13. Okay, so this is a little bit about ionization energies and atomic radius. We'll continue this in a later video.